In this video, we're going to continue to talk about catalysts and enzymes, and we're going to talk about another class of enzymes to start, and that are metalloenzymes. And these are 1/3 of all the enzymes in your body, and they use a metal ion to help with their catalysis. Here we're going to look at zinc, but there are other types of metals that are used in your body, like iron and calcium and so on. And enzymes, or metals in enzymes rather, help in three major ways. One, they can bind the substrate to help reorient them properly for the reaction to happen in the enzyme. Two, they could mediate redox reactions by changing their redox states. Or three, they can stabilize or shield negative charges, because metal ions are positive, so they can help to interact with negative charges. They can also bind to water, and once a metal binds to water, it will make the water more acidic. If you remember that from general chemistry, metals make water acidic. And for example, one reaction that needs metal ion is carbonic anhydrase, where carbon dioxide plus water makes carbonic acid plus a proton, the zinc helping make that water more acidic. It's polarizing the water. And so metals all in your body used for the enzymes in three general ways. Now let's just look in general, take a more general step back. How do enzymes actually speed up reactions? And we can point at four major ways it does this. One, enzymes bring substrates into contact with their catalytic groups or with other substrates. So this is a proximity effect. They're bringing things in proximity. This gives a roughly 5x speed. So not a lot, but still 5x. Two, enzymes will bring the substrates in the right orientation for reactions. So unless a molecule is a perfect sphere, which won't happen unless it's just an atom, molecules have direction. And so when molecules react, they have to be in the proper orientation. One thing that enzymes do is that they make sure they're in these proper orientations. And this speeds up the catalyst or the reaction by 100 times roughly. So this is the orientation effect. Three, if it's an electrostatic catalyst, that is, you have charge groups that will help to stabilize their transition state. So, positive, negative charges in your enzyme that will help your substrate go towards the transition state by stabilizing the transition state. And you can also get rid of water that enhances the speed. But the big thing that helps speed up reactions is by freezing any translational and rotational motions of substrates in the catalytic groups. Basically, you grab the substrate, you orient it correctly, and you make it stop vibrating and rotating as best as you can. This actually speeds it up by 10 million folds. So this is the big reason why enzymes work, because you don't have your groups changing bond length, you don't have your groups rotating all over the place, which allows for your substrate and your enzyme to properly do chemistry now. Now, this does have some penalties. So if we remember, delta G equals delta H minus T delta S. H is enthalpy, S is entropy. So if you're bringing enzymes close and you're bringing them in the right orientation and you're stopping their rotation and translation, well, you are making your substrate become incredibly ordered. And if you're ordered, you are taking a huge hit in entropy. So here, delta S is negative, which isn't good. To make up for that, delta H has to be negative, because remember, for a spontaneous process to happen, delta G has to be negative. So the way we overcome making our substrate stop translating and rotating is that you bind the substrate, and these positive binding effects, the free energy of binding, overcome this entropic penalty. So you're making hydrogen bonds, you're making ionic bonds, you're making van der Waals interactions, and all these are adding together to help overcome this negative delta S by making delta H negative as well. So the way that catalysts generally work, or enzymes, is that enzymes really want to bind the transition state of the reaction with greater affinity than either the substrates or the products. And the idea is the tighter they bind the transition state, the faster the enzyme is. And we can understand this by using this example. Let's say that we have an enzyme that's blue, and all along this enzyme are magnets, and our reaction is that we're taking a straight metal rod and we're trying to break it. Well, if our enzyme binds our substrate really well, so if it binds this metal bar, so it'll be easy to bind our substrate. However, how are we going to break it now? We are stuck in this straight conformation. So here's what our free energy looks like. The substrate binds, and then the enzyme substrate complex is very favorable, but look at our transition state gap. It is massive now, so we're never going to break our substrate. While if our enzyme is complementary to our transition state, so we might have weak binding. So here we have weak binding. However, we really want to bind the transition state because our magnets are positioned to bind the transition state. So this metal will be more likely to bend. So our delta G double dagger is much shorter if our enzyme looks like this than it does like this. That is, our reaction is faster because remember, reactions, the speed of reaction is determined on how big the slope is. So we'll break this and then we'll get our products. And knowing that enzymes bind to transition states more is the general idea behind inhibiting enzymes, which are good for antibiotics, therapeutics, agriculture, and general drug design. You're trying to make a drug that looks like the transition state because that will bind your enzyme. And if your enzyme binds to something that looks like the transition state but isn't, it can't do the rest of its chemistry, then it's stuck in that state. So for example, you can have proline be D instead of L, or you can modify your proline slightly by adding a carboxylic group and having a double bond here. All these things are very slight minor changes, but they are enough that your enzyme could bind these transition analogs, and it looks like our substrate, but isn't quite our substrate, and your enzyme gets stuck and is effectively a dead enzyme. That's one idea behind drug design. That's it for this video. I'll see you in the next one.